So I'm live streaming the webinar. Just a minute. How do I'll get a link very soon, which I will share with you, and then you have to send a mass email to people that if you can't join the meeting, please watch on this.
Yes, so let me just check if it's functional or not.
There is a link I got. Wait a minute. Naman, you are there in the meeting, right?
Yes, sir.
Yes, it's live.
Uh-huh.
I have the link as well, sir.
So now you go ahead, Pranav. Please inform everybody.
Sure, sir. Sure, I'll do that.
Inform everybody that if you can't join the meeting, please watch on this. Oh, okay. Dr. Prachi Kaul is joining the webinar. Dr. Prachi Kaul, welcome to the webinar. Good evening, ma'am. I can see you.
Good evening. Good evening, everyone.
Yeah, sorry for the glitch, but this is because of Zoom. So anyway, they have given us some solution. So we will start for today and then we will sort out tomorrow.
Wonderful.
Yeah, over to you, ma'am. You can start the welcome address. If you don't mind waiting, because there are only 140 people right now. This webinar can handle 500 people. So shall we just wait till, we have the audience there. In the meantime, may I introduce you to the others in the webinar. So Professor Barry Prentice from University of Manitoba is our Canadian connection. He is in many ways the man behind this webinar, this particular training program, because when I spoke to him, he was very supportive, very, very supportive. And he also has broadcast this information to Canadian colleges and schools. And among the speakers, Sohan, can you put your mic, put your camera on, please? So Dr. Sohan Suvarna is a young PhD, just finished his PhD actually. And this will be his first major activity, which he is going to work on. Professor Dhwanil Shukla, he is my colleague who is the co-PI of this particular webinar. So, and there is also Raman Verma, a very, very intelligent and motivated engineer. I call him as a problem solver. So you give a problem and he solves it.
Wonderful.
As you can see, he's sitting in the lab right now. So he lives in the lab literally. So these are the people who are going to conduct this 3-day workshop. We are aiming mainly to young students of engineering colleges. Yeah. And actually, we have opened it to anybody above class 10th actually. But most of the registrants are from 2nd year, 3rd year of engineering colleges, some from 1st year. But I have been speaking to some school teachers in USA, in Canada, and they are also propagating this message, and we expect to see a lot of those students.
Great.
Okay, Pranav Gupta is my volunteer who is sorting out the problem right now. He's sending a message to all the participants that if the number exceeds 500, don't worry, just join the live YouTube.
Yeah.
Another person is Namanuddin. You guys should start your videos when I mention your names. Okay, so Dr. Prachi, these are very young and enthusiastic people who are helping me out with this activity.
Wonderful to know this, and I'm glad that you have a team of young researchers and students, because they bring a lot of energy into anything that we start with. So that's a wonderful thing to happen for sure. Yeah. And intent is to, hear that anything that Shastri does also percolate down to the people who really need it. And as a matter of fact, if I I receive 1 rupee, I spend 70 paisa on students. So they are the future, So whether it is India or Canada or worldwide, they are the holder of future. So we must invest everything, whatever we can, in the youngsters.
True, very true.
Yeah.
So what I'm going to do is I'm going to change my background into something more exciting for the students. Give me that. Okay, so just a minute. You know what? I'll just share with you something else. So I had a discussion with the people from Zoom, and I said that, look, we are doing this event and not charging anything except the funds that we got from SICI. Why don't you give us an account? So they gave me actually a free account for 3,000 participants.
Oh, wow. That's
and
funny.
I tried yesterday. Yesterday we had a full dress rehearsal. Unfortunately, I don't know, for some reason today, when I started this webinar, it was not working.
Yeah. It looks like you have gone to mountain straight from Mumbai.
Yeah, I have gone to Manali from Mumbai. That's right. Yeah.
Or, Banff or somewhere hills in Canada.
Well, this was actually an airship that we flew in Manali for the DRDO in 2009.
Okay.
Remotely controlled, but this one is outdoor, and we are talking about indoor today. So what they did is they gave me on an emergency basis an account with 500 participants to sort out the problem. And I think by tomorrow we will have that account back.
Yeah, if there's any glitch, we are very happy to share our account with you. You can connect with us and we can use the Shastri's account, Zoom account for this purpose.
How many people can you handle, ma'am, on your account?
I think 500, yeah.
No, that they have given me. They gave me one with 3,000, which I was very happy, and I announced to everybody that we are going to get 1,000, but it didn't work somehow.
Yeah.
I'm surprised because it worked yesterday. We had a full dress rehearsal yesterday.
Yeah.
Okay,
it happens.
So, yeah, it happens. Yeah. So we have to be ready for all these, no problem. So finally, at least 500 people would be able to join. Okay, I think, ma'am, we can start. We can start the welcome address. People will join slowly, I think.
All right, good. So thank you so very much, Dr. Pant, for this opportunity. I'm very pleased to be with all of you. Those who have joined, very warm welcome to this workshop. I'm sure this is going to be really exciting activity, and you will gain much desired experience as you have, as you are wanting to from this particular activity. My name is Prachi Kaul, and I come from Shastri Indo-Canadian Institute. This institute operates on a binational corridor between India and Canada. We are mandated by both the governments, Ministry of Education, Department of Higher Education, as well as Global Affairs Canada, Government of Canada, which is the Foreign Ministry of Canada. We have been in existence for good over 50 years. In 2018, we celebrated our Golden Jubilee. It is important to highlight that for the youth who are joining here, that we are named after Shri Lal Bahadur Shastri, the second Prime Minister of India. What a noble soul he was, and the character he has implanted for the youth to follow is amazing, and we must try to imbibe at least a few traits of his personality. And as a matter of fact, the name that we are carrying with Shastriji's has a wonderful story. And briefly, I would like to tell you, because that is very interesting. He went to Canada to McGill University to deliver a convocation speech. And during the convocation speech, of course, was the present was Mr. Pearson, then Canadian Prime Minister. And Shastriji, our Prime Minister, Indian Prime Minister, thought, and this happened in 1966, and he thought that it would be wonderful to have a platform to carry out collaboration and cooperation in higher education and culture as well. And the thought was very well received by Mr. Pearson, the Canadian Prime Minister. And as we all know that soon after that, Shastriji passed away in a tragic incident. And as a homage to our Prime Minister, this institute was incepted in Canada by the Canadian Prime Minister. So we have our rootings there in Canada. But soon after we were incepted there in 1968, we opened our office here in India as well. So 2 offices, one in New Delhi, one in Canada. We were housed at McGill University for good 25 to 30 years. And then for admin reasons, we moved to Alberta province of Canada, and we are housed within the premises of University of Calgary. This is the historical background. We have a wonderful network of institutions with us, 170 from both the ends. So you name a good institution, it is on board. We are very, very privileged to have IIT Bombay on board as well. They were one of the founding institutions at the Indian end who joined the member council of the institute. What we do is very important for all of you to know, because as I got to know from Dr. Pant that most of the attendees are going to be young scholars. So we have wonderful opportunities for you to explore and get yourself enriched and experience it in India or Canada. So if you're joining from Canada or any part of the world and willing to come down to India, we have opportunities for undergrad students for internship. We have partnered with MyTax, and that enables greater participation of students for internship at the undergrad level. Similarly, at the grad level, there are doctoral and postdoctoral internships and research fellowships are available. If you are a young faculty in any institution, you also have an opportunity to go to Canada, or from Canada to come down to India and work with your institution of choice that are reflected in our network. And immense opportunities are there. We are not very particular in terms of defining it for any scholar. So it can be from developing a course with your affiliate or with your fellow colleague here in India or Canada, or developing a module to bring internationalization to your campus or to your pedagogy that you are offering at your institution. You can do a small collaborative research. There are opportunities for that as well. There are opportunities to build up your teams for the established professors. And as Dr. Raj was saying that he has a big team with young fellows and students. That's what Shastri nurtures, and that's what Shastri prefers, that you have a team of scholars who are bright and young so that they can be nurtured by established professors over the period of time, and then are able to take up the work that the professors have started. So these are the opportunities that we have with us. Along with that, we offer financial assistance, and primarily 2 ways. One is by offering the partnership that we enable is by giving financial support, and other is bringing connections. And Shastri strongly believes in people-to-people connect. And what today is happening is an apt example of people-to-people connect. Barry have agreed to be here with us because it's a connection that they have built. And I'm sure this connection is going to be lasting for forever now. With mutual understanding, they will identify each other's differences and complementarities as well, and try to help each other to imbibe the best that they have to offer, and whatever the enrichment they can share with each other. This is a wonderful initiative. As I got to know that there's so many registrations and people are joining, I can see the number growing. I'm not going to take much time, but I just want to say that the momentum have to go on. So this is just a beginning. Dr. Raj, I'm sure you will carry this forward if there is interest. And Shastri would be very pleased to support anything that helps you to build connection between India and Canada, especially amongst the academia and research fraternity. Learn from each other and take care of yourself. Have wonderful deliberation throughout. Thank you so much for having me today.
Thank you, ma'am, for those very wonderful words to start today's session. I wanted to quickly respond to the 2 points that you raised. One is we have a very young PhD who's looking for a postdoc opportunity in Canada also. And we have a young faculty, Dhanil. I'm sure they will take advantage of the various schemes that SICI is offering. And after this workshop, which is online, I am planning to conduct an offline workshop where some people can come physically and make these airships. So we will approach you later, depending on how this thing goes.
Yeah.
And definitely, I'm sure the Shastri Institute will support us. We are very, very positive on that.
Thank you.
So wonderful, and it's a very excellent start to today's deliberations. Okay, so I think we can then get going.
Yes.
So Dhanil, over to you for the initial
Sure.
introduction about the workshop. I'll just make some announcements for the participants. So as you have noticed, all the participants, around 200 now, are currently in the attendee mode. So if you have any query, you can raise your hand by clicking on the bottom. There is a button called raise hand. And you can also put your questions in the Q&A button. If you use chat, unfortunately, we'll not be able to respond. We can respond only when there is a Q&A or when a hand is raised. Okay, so I think we can start. Thank you so much.
Okay, thank you, Professor Pan. So we're just getting started with our 3-day workshop on design of remotely controlled airships. And let me quickly go to what is the objective here. So our objective is to spread awareness about lighter than air systems like the airship. We want to give you some basic training so that you can build your own RC airships. And we want to inspire you to find and develop some innovative concepts or applications based on lighter than air systems or related subjects. So welcome all for coming for this objective that we have. And other thing that maybe may motivate you to go through this workshop with more enthusiasm is that we are having our indoor airship regatta. So in June. And let me just play this nice introductory video for you. I'm not sure whether you're able to hear the audio also, but
So the audio is not
you should be able to.
there.
Actually, the audio is not really important. It's only a music. So
Yeah.
All right.
Yeah, it's just a music. So maybe you can just read through the text.
So if you don't mind, I'll just speak as it goes. So friends, this is the kind of airship that you are going to learn how to build. Okay. We are conducting an indoor airship regatta last week of June in the institute where I am in India. And we have a very beautiful indoor stadium. Okay, so this is basically for people who want to physically come over to the campus and attend that particular event. It's a fully indoor event. There's an indoor court, as you can see. And I'm happy to share that this activity is approved by the International Aeromodeling Federation. So anything that you do is going to be considered as a part of a world record. So this particular workshop that we are doing is essentially meant to give you a basic idea about how to go about designing an airship. And please register for the regatta on our website if you want to take part. Okay, anyone can take part. All we require is enthusiasm and passion and interest in airships. And we will teach you. We will teach you. Okay. Right? You will get certificates. And there are quite a few people from all over the world who are going to come in to conduct this event as well as to judge the event. And we have the support of the Aero Club of India, which is the national body of all aero modeling and flight related. We have a flight test engineer from Bengaluru. We have Mr. Mark Summers coming all the way from US only for this particular regatta to help us out. Okay, so what you want to do is try and take part in this activity. And this is the kind of airship that we are going to teach you in the next 3 days, including today, on how to build. I noticed that there is one hand up, Mohammad Wasi Ahmed. Mohammad Wasi Ahmed, we will allow you to talk. You can just unmute and speak. What is it you wanted to talk about quickly? Okay, so see, we don't have so much time, unfortunately. If you want to ask something, I have allowed you to unmute, but we don't really have. Okay, I think we can go ahead.
Sure. Okay, let's proceed from here. So, well, let me just give you an outline for the workshop. So day one, that is today, we will we'll have an introduction to airships, a talk on introduction to airships by Professor Barry Prentice. Professor Pant will teach us the basics of aerostatics. Dr. Sopan Suvarna will cover how to size or what's the methodology to size the envelope for the airships. Day two, that is tomorrow, we have Dr. Sovan again for making gondola, fins, and avionics. Professor Pant will show how to will show a tutorial on envelope sizing, and Dr. Sovan Suvarna again on demonstrating the sizing activity on spreadsheet. Day three, that is day after tomorrow, that is Monday. We have Dr. Sovan Suvarna on envelope fabrication. Then I'll be covering gondola and fin assembly. Mr. Raman Verma will show us avionics and system integration. And Professor Pant will show gas handling and flight tests. So this will be this is what we'll cover in the workshop in over 3 days. And let me just introduce you to the people who are the resource persons or the team that we have here, mostly giving this talks. So first of all, we have Professor Barry Prentice. So he's a professor in IH Esper School of Business, University of Manitoba in Canada. His research interests are transportation, trade, economic development, supply chain management, logistics, and innovation. Next, we have Professor Rajkumar Pant. He's professor here at IIT Bombay. His research interests are lighter than air systems, aircraft design, sustainable air transportation. We have Dr. Sohan Suvarna. He's a research engineer here at IIT Bombay in the same group. So his research interests are lighter than air systems, design optimization, flight dynamics, aerial robotics, trajectory planning, and as Professor Pant mentioned, he is just graduated as a new doctoral student. So I should say he has been instrumental in making a lot of the videos here. So next is Mr. Raman Verma. He's a project engineer at IIT Bombay, and his research interests are lighter than air systems, inflatable wings, multi-rotor UAVs, vertical takeoff and landing drones, and manned drones. Okay, and last, it's me. I'm Walid, and I'm an assistant professor here. My research interests are primarily low-speed aerodynamics, rotor wings. And with that, I think Professor Pant already mentioned some of the ground rules, like please use the question and answer tab for asking your questions, because the chat window will mostly be used for us giving out any notifications or urgent messages. In case you're not able to join the regular webinar on Zoom, you can watch the live telecast on YouTube. You may also share the link with your other friends who may not have registered but would still like to learn. So feel free to share the YouTube link. And it is mandatory to attend all the sessions, and only if you attend all the sessions sufficiently, you will be given the participate certificate. So please keep that in mind. And when you join the Zoom meeting, please make sure that the name that you mentioned is the name that is also the same in your when you register for the webinar, because that is the one that will show up on your certificates. Okay, so with that, thank you for your attention, and I invite Professor Barry Prentice to introduce us to airships. Thank you.
Yeah.
Yeah.
Would you like me to start now?
I'm not sure if I have to. Yeah. Professor Petrus?
Would you like me to start now?
Yeah.
Yes,
Okay,
yes,
well,
please.
well, thank you very much, everyone, for the invitation to speak today. It's a great honor. And it's also something that, you know, we feel a kinship between Canada and India as Commonwealth partners and a joint history. And of course, we have many people from India now living in Canada, colleagues that I work with every day. So this is a special sort of opportunity, and I really appreciate the invitation. I'm going to share my screen now to bring forward my presentation. With a bit of luck, it'll come up. There we are. I assume you can see it now?
Yes, we can. Yes, we
Very
can.
good. So what I'd like to talk about today is really an introduction to explain why you should care about airships, I suppose. I want to talk about some of the various designs that are being proposed today for the 21st century, but also how we got here, and a little bit about the economics of airships. They're a very unique means of transport. They have a special role in the world, something that is different than other modes of transport. They can fill certain needs which are very important for us to look at. So I'm going to start with this chart. Here we have about 300 years of history in one slide. So I'll go through it pretty quickly. It really starts out, of course, with the Montgolfier brothers in France, who had the first balloon based on essentially hot air. Moving on to the discovery of hydrogen, and Professor Charles and Roberts, who had the first hydrogen balloon they flew. Of course, we had the first flight across the English Channel. This is, again, 1785, a long time ago. The airships played a role in the Paris airlift in 1870. Again, that was sort of the first use of airships as a strategic military tool. The very first real airship, although we did see one that was used in 1854 by Henry Gifford. The difference between an airship and a balloon is that you have a power to move it. Of course, it wasn't a true dirigible because the engine was too heavy and not powerful enough to move the airship. So it wasn't really considered the first airship. That honor went to Santos Dumont, who had the first controllable airship flown in 1901. Very quickly after this, the technology accelerated. And you can see that by 1919, we had an airship that flew both ways across the Atlantic. This is the very first aircraft to do that. 1926, we had the very first aircraft to cross the North Pole. In fact, the first persons to cross the North Pole were in an airship, the Norge. 1929, we had the very first circumnavigation of the planet by an aircraft, and that was the Graf Zeppelin. Of course, we had the R100 came to Canada on a flight and a return, a very successful flight. 1935, we saw the Zeppelins crossing the oceans, going to the New York in the summertime and coming to Brazil from Germany in the wintertime on a regular service that was kept to a schedule. These vehicles could fly at 145 kilometers an hour, and they had a useful lift of about 70 tons. So think back to that, well over 85 years ago, we already had airships of this size and regular service that was offered. Of course, the war came along and intervened, and it had a very pronounced impact on the airships. The last of the rigid airships was built before the Second World War. During the Second World War, the Navy blimps, these are inflatable type airships without a frame, were very successful in terms of submarine, anti-submarine warfare, and for patrolling with the convoys to protect them from the enemy submarines. That service ended about 1962, And then there was a period where there was only 3 airships in the world, and those were the Goodyear Blimps. In the 1970s, we started to see interest gain appear, partly because energy prices had soared. In fact, the 1970s and the 2020s have a certain similarity to them that is quite striking, with rising energy prices and concerns of inflation. We're now seeing, I think, more interest in the airships again. But in the 70s, there was a burst of investment. The Skyship 500 was the first of the modern airships or blimps that came along. And that was quite successful until the oil price went down, and then interest disappeared until the year 2000, when the Zeppelin company, which did not disappear with the war, and they survived the war and prospered thereafter, but saw no market for airships. In the year 2000, to honor the founder, they built and flew the first new airship, the Zeppelin NT. This is an airship that actually has a frame inside, unlike the inflatable blimps. And then the next milestone, I think, would be in 2016, the Airlander flight, which we saw the first full-sized airship, and this one is shortly to go into some form of production. So to give you a quick history of airships, you can see they've been around a long time. They were actually very successful. They established records that have yet to be broken. And of course, they set the groundwork for where we are today. So what I'd like to talk about today in part is the search for a dominant design. We've had 85 years since the last rigid airship occurred. And today we can look at structures. They can be rigid or they can be inflated. Obviously, for the small blimps or airships that are going to be used for the regatta, they must be only the inflatable kind, because there's an issue of trying to overcome the dead weight before you get useful lift. You can't do that at the small size with a rigid airship, only an inflatable one. In terms of control for the airship to go up and down, because you have a constant lift, which means that if you take load off, you have to put something on, or else you just keep going up until, I suppose, the airship finally would burst. There are several ways of controlling this. You can put on ballast water. If you take off your load, you can compress the gas, you can heat the gas, you can vent the gas, and of course, you can also use your engines to move you up and down. In terms of shapes, most of us may be more familiar with the cigar shape of the old Zeppelins, but it can be a catamaran shape, and also there's work going on for disc-shaped airships. In terms of flight controls, and I know you're going to be getting into this, you can have fins and thrusters, or a combination of both. The lifting gas can be either helium or hydrogen, and there's certain benefits to each of these. In terms of metals, we can have certainly aluminum is a common metal used in building the rigid airships. But today we have composites, and also even the future of nanotubes. Materials are getting lighter and stronger, and this is very good for airships, which of course, every kilogram of extra material you have for the structure is a kilogram of cargo you can't take. In terms of propulsion, turbines, diesel motor engines, or the future certainly is what everyone is talking about now, is electric, because of carbon emissions. Finally, we have some human factors. Piloted airships are certainly the way we are today, but everyone is looking at the future for unstaffed or unmanned aerial vehicles. Drones, I guess in the popular lexicon, will be the way airships are likely to fly in the future. In terms of manufacturing, obviously, many advances there. Maintenance, inspection, and finally, my bailiwick is cost and performance, and I'm going to speak a bit more about that later. So in terms of these structures, you could think of cigar-shaped. Rigid airships often take this form. The catamaran, sort of a semi-rigid structure, and of course, lenticellular is another form. These would be the circular type, or the disc-like airships. In terms of airships themselves, as I mentioned, the very small airships, you are left with only blimps or inflatables. You can't overcome the weight of a rigid airship at a small size. So at a certain size, the blimps dominate. So what we see for the advertising airships, they're all inflatable types. But the largest blimp ever built was about 15 tons. Once you get beyond that size, then it's likely better to go with a rigid airship. And in fact, there seems to be some material limits at the present time, even to get beyond this, the hoop stress of the materials, which limit how big you can actually build an inflatable. Whereas the rigid airships, we know they got to 70 tons. What we don't know is what the upper limit is. And that upper limit could be into the 100 tons, 200 tons, 300 tons. We don't know. What we do know is that the bigger the airship, the lower the cost per ton of movement. They are like ships of the ocean, so they have very much increasing economies of size. Amongst the rigid airships designs, these are a few that are being proposed. The Aeroscraft, this was a full-scale model that was built and briefly flown. We have LTA Research, a very secretive project going on with the founder of Google, Sergey Brin. Flying Whales from France, who is very much in the process of their design, building a hangar at the present time to construct their airship in France. This is the Bassy airship. This is the only Canadian airship company, really focusing on an airship for cold weather and for Arctic applications. The British airship Varialift started in France, but they are moving back to Britain, as I understand it. An all aluminum airship, and they're looking at compressing helium as a way of controlling their buoyancy. And this is the or Atlas, which is from Israel, based on Russian technology originally. And you can see it has a catamaran sort of shape. Other catamarans, the Lockheed Martin has flown this airship already some over 10 years ago. Aero's vehicles, a US design being developed in Argentina. This is the LEM-V, which was designed actually for the US military to use for surveillance in Afghanistan. That project terminated when the war changed, and it was purchased back by the builders in England. And this is the Airlander today, is based on this design. And finally, we have in Brazil, Airships do Brazil. We have a number of disc-shaped airships or lenticellular airships. Quite a few of these are coming out of Russia. At this point, I believe they're all in design. Luftships is another venture coming from Germany. So what you can see from this little display is that we have interests around the world in airships and a number of different designs of airships that are being considered. In terms of buoyancy control, again, to just reiterate slowly, in terms of changing the weight, if you have cargo to put on, you don't need to worry about ballast. But oftentimes it isn't possible to find appropriate cargo or enough cargo, so you must top up the load. The easiest thing to use is water, because it's very indivisible or very divisible. You can pump it very quickly. It's inert, and water is everywhere. So this is the most favorite type of ballast. But in some cases, maybe you don't have access to ballast, depending on what you're doing. And I'll come back to that in a minute. So we've been seeing airship companies looking at different designs. The Russians had looked at heating the gas. The British airship is looking at compressing the gas, as is Aeros in the US. And of course, finally venting the gas. This was used very widely by the Zeppelins when they were using hydrogen. That process was discontinued when everybody switched to helium, mainly because the gas is so expensive that you couldn't afford to vent it. But as we are looking at returning to hydrogen, this is likely going to be one of the ways in which we will adjust the height of the airship by changing its buoyancy. And finally, of course, you can use engine propulsion to push you up or push you down. and aerodynamic lift. Any airship design, if you point the nose up and you power the engines, you will get a gain in altitude, and vice versa if you point the nose down. So aerodynamic lift is also part of any airship. This is the design for the Airlander and the Lockheed Martin, and several of these, what we call, they refer to them as hybrids. I think catamaran is a better description, because what it is like two cigar-shaped airships side by side and then covered in total. Part of the reason for this is that by having a smaller diameter, they can avoid some of the hoop stress. So the hybrid design can be made bigger than a blimp of the same sort of size and length. In order to adjust, they also are heavier than air, maybe 20 to 30% heavier than air. The notion being that they will use their engines and the aerodynamic shape of the hybrid to get aerodynamic lift as well as the lifting gas. And then when they drop off a load, they won't have to worry about putting on a ballast. They could be able to fly home directly. This would be a very important feature for an airship being used for humanitarian logistics, where you don't have a prepared base you're going to, or anything to put back on as ballast, or certainly in a military circumstance, which is what this airship was designed for, to bring in supplies behind the lines, drop them off quickly, and then return for another load. This is the design for the Varialift, which looks at the compression of gas. They have these cylinders on board. So essentially, when they want to go up, they would release gas from the cylinders, expand the volume of helium inside the shell of the airship, and of course that would displace air and give you lift. When they want to come back down, they'd reverse the process. They would start to pump the gas from the large cavity back into the pressure tanks, and as the displacement is less, the airship will come down, and you can see how that would move. So they're looking at a vertical landing and takeoff, and of course, again, the ability to land anywhere and not have to worry about a ballast load going on. Of course, the last one I mentioned was the venting of gas or water ballast, and this is a picture of the R100, which did fly to Canada very successfully, and you can see that it's releasing water ballast at this time. Obviously, it is doing that to gain some altitude. If it wanted to come down, it could release hydrogen to make the airship heavier and to return back to Earth. I want to speak a little bit about landing and mooring. This is one of the problems that was not really conquered in the previous generation of airships. The Germans did have a system based on a railway track, a circular railway track, with a car attached to the tail and the nose to a mooring mast, and that kept the airship on the ground. But on the ground, airships are more vulnerable, and also, of course, they're a very large structure, so they are unstable. If the wind changes, the nose of the airship is going to turn into the wind, which is why you see airships moored at masts. The difficulty is for loading cargo on and off, you also have instability in terms of pitch. The airship can move up and down at the mast. So the railway car and the circular track allowed the old Zeppelins to be held steady on the ground for refueling and for changing pastures. This sort of design would be necessary for any cargo movements. Again, you have to think about the safety of the people on the ground. You can't have the airship moving. It may be lighter than air, but it has a very large mass. So nothing is going to stop it in its path if the wind is pushing it. Our proposal is to use essentially a turntable. The airship lands vertically onto the turntable. Once anything is on the turntable, if the airship moves, the material of the ground handling crew and the forklifts and other things move with the airship, so there's no risk to the airship or to the ground handling crew. And this is a much smaller footprint than trying to build a railway track in a circle around the airship. The other approach to landing airships is an autonomous system. This is what's being favored by the Lockheed Martin, the Airlander, the Atlant, and also the Aeros companies. Essentially, they're looking at modified hovercraft pads, so the air will blow down when they want to move around on the surface of the water or some concrete surfaces. And when they want to hold their position, they'll reverse the fans and pull the air through the vents, so that it'll be like a large suction cup or suction cups that will hold the airship steady while a ramp would lower down and everything would come on and off the airship that way. Again, this has been developed and it has been demonstrated at least at a certain level that it will work. It has advantages and disadvantages. Obviously, this adds a lot extra weight to the airship, a lot of moving parts, extra fuel, and of course, maintenance that goes with this. But it does have the advantage that, of course, you can land anywhere. So depending on the mission, this is an excellent design for certainly military use and also for humanitarian logistics. I want to talk a bit about the economics of the airships and where they sit. What you can see along the one side is the speed of the transport, and here we can see the fuel consumption. Obviously, the faster you go, the more fuel you're going to consume. That's pretty clear. So helicopters and airplanes are fast, but they consume huge amounts of fuel and produce a lot of carbon emissions at this point. The airships are sort of in the middle. They are faster than certainly any of the other modes of transport, trucks, rail, or ships. But of course, they do have some disadvantages, although I would say that this chart is a bit misleading because fuel consumption of an airship can be certainly lower per ton depending on its size. But generally speaking, you're going to see more fuel consumption relative to certainly a railway or a ship per ton that's carried. In terms of size, I mentioned earlier about the bigger an airship is, the better it is. And this is the economies of size or the square cube rule that follows structures where if you have displacement vehicles and you double the lengths, you increase the surface area by 4, but you increase the volume by 8. So this is an illustration of tankers, and you can see that a tanker that is carrying 4 times as much from this 100,000 deadweight tons to 400,000 deadweight tons, it only increases in length, maybe by a quarter. Of course, it gets larger in the other dimensions. Similarly with pipelines, by doubling the diameter of the pipeline, you increase the flow through that pipeline much larger than just double, triple perhaps. And of course, here is a famous picture of the Graf Zeppelin beside the Goodyear Blimp. The Goodyear Blimp will carry about maybe 1 to 2 tons at the outside. It's about 250 feet long, I'm not sure in meters. The Graf Zeppelin, which was closer to 800 feet long, would have a lift of about 60 tons. So you can see that as the airships get bigger, they get much better. And of course, this is a huge advantage for freight transportation. There also are other trade-offs that are interesting. The airship requires no energy to stay aloft. It floats just like a ship of the ocean. Its only fuel consumption is a function of its drag and how fast you go. So if you go at a higher speed, you can, for a shorter distance is good, but if you want to go a longer distance, if you go at half the speed with the same fuel consumption, you can go twice as far. Of course, from a utilization perspective, how many ton miles of goods you carry, if you are going faster, you're making more trips, you carry more ton miles. As you slow down, you go further, but you're also losing some utility. So your ton miles declines as you go at a slower pace. In terms of any transport vehicle, we have to think about the round trip because the airship costs to go full or empty basically are the same. And you can't go empty, you have to have a ballast on load. So you're always carrying a load. The question is whether it's a paying load. And in economics of transport, what we call the front haul and the back haul aspects of the trip that has the more freight, this is the thicker line, is the front haul. The one that has less freight, of course, is the back haul. And the trick to high profitability in transportation is to have loads in both directions. Not always possible. And in any case, you typically have less in one direction than the other. So you have one more profitable route than the other, but the idea is to get enough revenue for the round trip to pay all your costs and have a profit. In terms of airship markets, I want to go briefly over this. We can think of four, which I'm going to illustrate here, short haul and long haul general freight. So general freight being everything you can imagine that would be moved, that could be put on a pallet or would fit into a tractor trailer box. Of course, you can also have other things in there, live animal transport. Cattle and hogs are moved in trucks. They could be moved in airships, and fuel could also be moved, in this case, either with a bladder or a tank inside the airship. Project freight and aerial craning is another market. This is typically a fairly short haul market, although it could be long haul. And the issue here is to have an airship that would be able to bring in a large piece, typically overweight and maybe overdimensional, and be able to land it vertically in its spot and then go back and get another load. Examples of this could be an electrical tower for a hydroelectric or for an electrical transmission line. It could be a large transformer for an electric dam. Could be a wind turbine blades. So many things in this project freight area. In fact, one of the things that's interesting could be a large tank. I recall a situation where there was a large tank for brewing that was shipped from Germany to Canada by ship. It came into the Hamilton Harbor, and then it had to be moved very slowly by truck through the roads, taking down electrical wires, moving only at certain times. It took longer to go some 70 or 80 kilometers across the land than it took to come all the way across the ocean by ship because it was such a slow, painful move. This is the kind of move that could be done very quickly by an airship, including, of course, even moving whole houses. It's quite possible to think of houses being built in a factory much more efficiently and then lifted off and put onto a foundation by an airship. Resource extraction, another market for mining is the main one perhaps we think about here, where you have to bring raw materials from remote locations. Probably it would need to be concentrated, so you're not bringing rock, but you'd be concentrating the ore into maybe a 25% metal, and then bringing that out to a location for transshipment. And then finally, the emergency and military missions that I have mentioned briefly earlier. So these are, again, for the short haul markets. The needs of the airship, it should be streamlined. You're going long distances and speed is important. So the more streamlined the airship is, the less fuel it's going to use. So most likely airships of the cigar shape style will be used for long haul freight movements. And of course, the question of long haul is how long? And it depends on the size of the airship. What we have found in our research is that you have to actually have a fairly large airship to compete with long distances. something in the order of 100 tons lift would be necessary to compete crossing the Atlantic or the Pacific Ocean, and preferably something in the 200 tons size for the Pacific Ocean. But if you have only a 30-ton lift, it's surprisingly, if you want to compete with land-based transport, how short your actual distances are. Clearly, this sort of transport is going to be palletized, although you can move sling loads as well. You'd like to have some climate controlled space. One of the largest markets, I believe, for these sorts of airships would be moving fresh fruits and vegetables. We move them now in refrigerated trucks, but oftentimes we're limited to land routes that only allow us to come relatively short distances. With an airship, of course, they could fly vegetables from Africa across the Mediterranean to Europe. We could bring in fruits and vegetables to Canada from South America or from Central America, the Caribbean islands. And certainly in India's case, being able to move products from India, perhaps to the Middle East, to other parts of Asia would be, or Europe for that matter, would be a great export industry for India. Rapid and safe ground handling is important. Again, an airship only makes money when it's moving with cargo. The less time you're on the ground, the better it is. But also, of course, from the perspective of the airship, the only risk to an airship is when it is at or close to the ground. When it's in the sky, it's very safe. On the ground, you have to be more concerned about winds and so on. And of course, all-weather reliability. If you're moving general freight, companies are expecting you to be on time because the systems are set up to minimize inventories, to be just in time. And so all-weather reliability is a more important issue in general freight. Some issues, of course, competitive rates and times. We are competing with other modes of transport. In some cases, it's unique, but not all. Moving dangerous goods, it's not clear whether airships would be permitted to move all dangerous goods. Perishability, and of course, the issue of ballasting. What are you going to put back on if you take off your load? These are some of the project freight designs, and again, there can be several. It could be the disc shape design for project freight, but also this is envisioned for the flying whales vehicle, which has got the ability to load and unload from the air. At least that's their design, to do that safely, which would be very desirable for moving wind turbine blades or any project freight. Also, of course, they're looking at using this airship for harvesting timber. This is the Atlant, again, a similar design in mind. This is a kind of a multi-use airship. They could be used for longer distances, for emergencies, and for project freight. So they're sort of covering many bases at once. As you can see, the needs, a flexible cargo configuration. Balance is always important in an airship. So you have to be able to balance the load. Long endurance, again, these may be slow moving. Certainly some of the disc-shaped airships would be in that category. Being able to hover and hold a position. One of the advantages of a disc shape is that if the wind changes, it doesn't affect the orientation of the airship. Whereas in the Flying Whales airship, they have many fans. You can't really see them in this diagram, but many fans that are there to just hold the position of the airship for precision loading, unloading. And of course, the issues being safety and ballasting. Once you drop off the load, you need to pick something back up. And how exactly that's done is more difficult to envision for the three bottom categories. In the case of the Atlant, it is heavier than air, so it'll be kept aloft by its engines. And if it drops off the load, presumably it'll be able to fly back and land safely. Resource extraction, again, we have the Flying Whales. You can see they're showing how they would pick up lumber, flying in this mountainous area, inaccessible areas, of course, and we have many. Another design that came out of Canada was a spherical airship. And There are logging balloons, and many people have discussed the notion of using a spherical airship and perhaps a drone type airship. In fact, it would be a drone airship to go and pick up logs or other materials and ferry them back to a transshipment site. Again, needs we have, hover control is absolutely critical, and vertical offloading. Cost is always important depending on what you're moving, and a drone capability would be very desirable because you're just going back and forth and probably relatively short moves. Issues again are ballasting and transloading. How you do this and how do you do it effectively and efficiently and quickly is a question mark. And then finally, we have the humanitarian and military applications. Obviously, the autonomous landing is a very important feature because you never know where you're going to be going and what is in front of you. Eliminating the ballast and being able to self-ballast is a very desirable feature because you don't know if you're going to find something to put on after you've dropped off your load if you're coming in with a traditional airship. These would be required for long distance transport. Again, going to the site of wherever the emergency is, it'd be important that you have long distance capability and perhaps flying a bit faster than a traditional airship. Again, they're using the engine thrust for lift as well as forward movement. This does mean that they burn more fuel, quite a bit more fuel, because they're obviously using that aerodynamic lift as part of their transport, and you have to pay for that. Flexible cargo capability would be very desirable. And the issues, of course, utilization. This is an issue for all vehicles, but certainly, and you have specialized equipment like this, how many days a year do you actually have paying loads? And you have to look at the economics of your airship and the basis of how many loads can you get, and also what will people pay. Obviously, in the case of the military, they're not too concerned about economics. In humanitarian logistics areas, being able to complete the mission is more important than the cost of human lives are at stake. So with that, I will stop at this point and welcome any questions from the audience. Dr. Pant, I'm not exactly sure how we're going to handle these. If you want me to try and read them in the questions, or if you will read them and pose them to me, whichever works the best. I'm pleased. Thank you.
Don't worry. So many questions we have already answered while you were presenting. Many, around 15 questions have already been answered. But there are some students who have raised their hands. I would request students to ask their questions by typing in the Q&A. So Girish has a question: is hydrogen being seriously considered by anyone? The answer is yes, and we will talk about it on day 3. Yeah. My request is, let the questions be related to only what you saw and what you what was presented. Don't ask questions which are beyond the current presentation, because this is only the first lecture of the 3-day workshop, right? So there will be many occasions for you to ask questions. All right. So Omkar Lad, you have raised your hand, but can you please type your questions in the Q&A, because we will not have time to take questions like this from every individual. If you have any question, Omkar and Kaushik Senapati, please type them in the chat in the question and answer, and we will take them up. Yes. Solar powered airship is available. Yes, Kaushik, the answer is yes. We are working on that in India also. And there is going to be a race of solar powered airship across the ocean. I'll talk about it later on. Good question. Once again, let the questions be limited to what you saw in the presentation so that the speaker can answer those doubts.
I didn't mention anything about solar powered airships. Obviously, it's a very big surface area and you could use solar power. What you have to always consider is the weight that you're adding to the airship versus the energy you'd be collecting. And there's an economic trade-off. Does it make sense to use the extra weight for moving cargo that you would have from the weight of the solar panel, So this comes back to the efficiency of the solar collectors. Generally speaking, my understanding is they get heavier as they get better, which is not a good thing for the airship. And also, you only have the energy when the sun is shining. So you still have to have a backup energy regardless. We are looking at using solar strip across the top of the airship, but not necessarily for powering the airship except for emergencies. It's there really to remove any snow or ice that might accumulate, because the airship obviously will get heavier if you have ice and snow building up.
Right. Oh, okay. So, see, there are people who are asking very general questions like, what is the future of conventional airships in India? Now, we can't answer this in such a meeting. So, Kamlesh, we cannot answer such questions here. There is a question about from Ajit Chetri about all-weather reliability. Except density variation, is altitude variation or increase good or bad for airships? Barry, could you like to elaborate on that?
Sorry, is it radiation?
The altitude variation, that means change in the altitude. Is it good or bad for airships?
I still don't know if I understand the question.
The
Maybe
altitude variation.
Oh, altitude.
Yeah.
Well, essentially, you want to fly as low as you can in an airship because the air is thicker. And the airship's weight is a function of the weight of the air that you're displacing. So as you go higher in altitude, the air becomes thinner and you're displacing less, which is why also you have to have space inside the rigid airship for your gas cells to expand. You don't have them fully expanded on the ground. As you go higher, the air becomes less dense and the gas will expand because there's less pressure. When you have full expansion of your gas cells, it's what we call the pressure height. And every airship has a maximum height that it should go. Typically in airships, I would say you'd like to fly something below 2,000 meters, maybe 1,000 meters. And the pressure height, you probably wouldn't go any higher than a maximum of 3,000 meters. And again, the desirability of flying low means that it's better to fly across oceans. Mountain chains are probably something you don't want to cross if you don't have to. And the airships will likely go around mountains rather than trying to even go through them because the winds and the passes and so on are more dangerous.
Yeah, that's wonderful. Srujana wants to know, how is mooring used in airships?
Mooring the airships. Yeah, this is again, ground handling is one of those areas that needs work. And what has been done traditionally is to bring the airship down and attach it to a mast, which is just a very tall pole in the middle of the field with no obstructions, so that the airship can weather vane around the mast, move some 360 degrees. Whatever the wind is blowing, it'll move. This is okay, but it isn't very efficient in terms of any kind of cargo exchange. It takes time to bring the airship to the mast. It also is somewhat dangerous because depending on how fast you're moving, typically they would have a cable system where they would winch the airship to the mast to be able to control the speed at which it's coming. You don't want the airship running into the mast. And there are some accidents that in the past we saw, but you still have the difficulty of pitch where the airship is moving up and down at the mast. I think we need to have a way of controlling it. So again, we look at the turntable as a solution to that. It may not be the only solution, but I don't think we can just simply have a mast and then load cargo on and off an airship.
Okay, I'll read some few questions. There was one question by RP from Los Angeles about sloshing in the ballast tank when you have water.
Yeah, well, it's a very good point because again, the airship balance is important. One thing to remember though is an airship isn't like an airplane. It's very stable. When you're in the air, nothing moves quickly in an airship. So if you're going to see the ballast water move, it wouldn't move very fast. Of course, that being said, you could hit an updraft or something that causes the airship's nose to rise, and then you might have the ballast water sloshing the tank. Obviously, you'd want baffles is one way of controlling the movement of the water in the tank. It may also be that you would have the water much more distributed around the tank. We've got some certain ideas about that, how you control the ballast water. And of course, we also are concerned that you make the ballast water doesn't freeze. If you're in a cold temperature climate like we are in Canada, we have to be concerned to keep that maybe the water moving or keep it from getting too cold. That would be another issue for ballast water. I should also add to that, moving water from one place to another. We have to be concerned about introducing foreign organisms. And so the ballast water has to be clean. That may not mean more than treatment like you would with a swimming pool to make sure there's nothing living inside that ballast water. But it's again a consideration that has to be borne in mind when you're moving water around.
Right. There is also a question, a very good question from Frank Neumann. He's asking about, there is a trend towards unmanned smaller scale airships for much lighter loads, some using solar power. Is there a business economic viability of these carriers?
Well, this is something that you have to work out, I suppose. But first of all, the drone technology, clearly that's the way of the future. There's no reason to have a pilot on board per se. Nothing happens fast on an airship. But you do have to have a pilot on board initially to train the computer to fly the airship. You can't just immediately put a drone on and say, okay, fly. So there has to be a pilot at least at some stage and teaching the computer how to fly. Once that's done, of course, yes, you can have drones. In terms of size, it's important to remember that the bigger the airship is, the better it is for a number of reasons. One, of course, is more economic. The larger it is, the more cargo you're going to carry relative to the purchase price of the airship. It just takes less materials to build a bigger airship per ton of movement. It's also important to recognize mass. The lighter an airship is, the more sensitive it is to the winds. The small blimps, they're very good. They're less expensive to build. You can build them smaller. The trouble is that they're very sensitive to the winds. And so landing and takeoff in the winds is a bit of an issue. And certainly in high winds, you have another problem. A large airship like the old Zeppelins, yes, the wind would push them around, but it would be very slow in moving. And so you have time to react with your engines today, with vectored engines and computers that are pushing the airship, countering the wind and wind gusts. But this would be easier the larger the airship.
Okay, that is a very critical question. Why blimps and airships have died out and how they might make a comeback?
How do we make a comeback for the airships?
Yeah.
Well, I think, in part, there's two things that are pressing upon us. One is climate change. We know that the carbon emissions are leading directly to higher temperatures on the Earth. And this is a real problem that we're facing for a number of reasons. I mean, you can pick any one you want. The loss of glaciers on Antarctica, which could raise the sea levels and affect our ports. It could be the melting permafrost we face in the north. It could be heat waves that kill crops and even make some places on the Earth uninhabitable just because the temperatures are too high. We have to stop burning as much carbon. And if we look at air transport and air freight, which is a very desirable and fast growing area, most of it's being done with jet airplanes. And the jet airplanes, first of all, these are typically older airplanes that have been converted from passenger to cargo use. So they're the the oldest technology, the most polluting, and very little freight actually needs to be flown at 800 kilometers an hour. Freight doesn't complain, and as long as the customer is receiving the goods within a reasonable time, so if you can cross the ocean in, say, the Pacific Ocean in 4 days or 5 days versus a ship that would take over 20 by the time it goes through the port, well, that might be fast enough. You don't have to do it in 12 hours as you would with a jet airplane. So in terms of the economics and the markets for airships, we need these craft to replace jet airplanes for cargo purposes. I would say the other reason for airships is to be able to go places where the traditional transportation can't go. We can't build massive, long, paved airstrips in remote areas like northern Canada and fly in with jet airplanes, but they're just too expensive. Whereas you can bring in large loads with an airship, and load size is important because many things are indivisible or bulky, and they're not really suitable for airplanes.
Okay. Well, there are many questions. Many of them are very general in nature, so we don't really have to answer them. Okay, I'll just read out a few of them. What is the maximum possible speed of an airship, both theoretically and practically?
Well, I suppose theoretically it's that they say you can fly a brick if you put enough power on it. So I don't know what the upper limit of an airship speed is, but I can tell you from an economic perspective, the faster you go, the more fuel you burn because of drag, and it's an exponential function. What the old Zeppelin company found was that the sweet spot in terms of sort of the economics of travel was about 150 kilometers an hour. Now, we're not exactly certain whether that was the maximum or the cruise speed they chose because that was all the engines could produce in terms of power, whether it was the most fuel efficient spot, which I'm sure they had figured that one out and that was important to them, or it was the airframe. And the airframe, they didn't want to push it faster because they were not certain about the strength of the airframe. Today, we can do that much better. We have computerized systems and strain gauges and brilliant engineers, some of them on this call are, and we can make an airframe that I think will stand much higher speeds. But that question mark as to what is the fuel consumption versus the payoff, it really is an empirical question. It needs to be studied. My belief is that 150 kilometers an hour is easily an attainable speed and one that would work, but we could see airships flying up to 200 kilometers an hour, maybe a little faster. But you have to remember that an airship is efficient because of the weight of the air it displaces. And the thickest air is at the lowest level. And if you're flying through the thickest air, you're getting the most drag. So hence, if you want to go faster as a jet airplane, it's great to go to 30,000 feet because the air is thin and there's less resistance, but you're not going to get the same lift from the airship at 30,000 feet. In fact, you will get very little, I suppose, relative to flying lower and slower. So in sum, you can certainly look at 150 kilometers an hour as a reasonable speed. We'll see if it goes a bit faster or slower depending on the mission of what you're carrying and how far you're going.
Okay. We have, I think, another few minutes to take some questions. There are questions like, some of them are not worth discussing. Can you tell me generation of power using airship, is it economical compared to conventional power generation? Generation of power using airships, we never talked about it.
Yeah, well, again, we actually believe that the old Zeppelins were underpowered. They had very heavy engines, diesel engines. They weren't very efficient, and they had to be concerned about their weight. So they didn't have maybe as much power as they should have had. Certainly, you'd want to have enough power to make sure that your airship was always be safe. You get into circumstances where you need more power, you have to have it. You may not use it all the time, but you'd want to have that reserve power available to you. In terms of the maximum power you need, since your lift is free, you're not using any power to stay in the air, unlike an airplane where about half of the energy and power is consumed just to stay aloft, and then the rest of the power is to push it through the air. In the case of an airship, you're only looking at forward movement, and hence the fuel consumption is less and the power requirements are less, but still they are fairly substantial because they're very big machines. What we're looking at is electrically powered airships, or propelled airships, I suppose you should say. They will be some form of probably hydrogen fuel cell or hydrogen turbine powered electric generators to drive the motors. Batteries don't really make a lot of sense because of their weight. They're just too heavy and the range would be too short. So that's what the future is looking like.
Okay. I think, okay, so some questions are very general. I mean, I don't know how do we answer. What are the design strategies for airships? I mean, what can we do with these questions? But yeah, we will try to answer them as we go. I think there are other people who are answering these questions, so let them be answered. I would like to move on. Thanks, Barry, for your very nice introductory talk about airships. So I would like to now move on to the next talk, where I will be sharing my screen to talk about the basics of aerostatics. So a request for people to just confirm to me that the screen is visible so that I can go ahead.
Yes, the screen is visible.
Okay, great. So friends, many of you have asked questions regarding the working of airships. The main governing principle of airships working is what is called as aerostatics. Now, the word aerostatics is a very interesting word in aviation because it talks about something that generates aerodynamic force even when it is static. Okay, and the only way in which you can get force when you are static is either magnetic or, as we will see today, the buoyancy. So the working principle for airships is buoyancy, which, as you know, is a tendency of a body to either float or sink in a fluid. So air is a fluid and airship is a body that literally floats in the fluid. Now, when we look at any body and any fluid, such as you can see on the left of the screen, certain objects like a plastic bottle or a rotten fruit, when you put them in water or in a water body, they float, whereas there are some things like a brick or a heavy anchor which is unconnected, they will sink. So whether a body floats or sinks depends on a principle which was discovered by this gentleman called as Archimedes. And you all know the story, I'm sure, about how he discovered this principle when he was having a bath in a bathtub. And he looked at the fact that when you lower your body in a bathtub, the water level rises and some of it falls off if the bathtub is full almost to the brim. And with that, he got an idea after shouting Eureka, and he gave us the principle which is called as the Archimedes Principle, which says that a body immersed in a fluid is subjected to an upward force. That upward force, Archimedes argued, is equal to the weight of the displaced fluid. So if the weight of the displaced fluid is more than the weight of the body that is displacing it, the body will float. And if the weight of the body is more than the weight of the fluid it displaces, then the body will sink. That's what it is. So what is buoyancy? So any body which is in a fluid, it has pressure forces acting on all sides. Here we are looking at a small cube. So there is a force acting on the top called as F top, which is at the height h. Then there is a height h plus L, where L is the length of the body. And the force on the bottom side is F bottom. So since the pressure of the fluid, so the upward net force on objects within a liquid is the buoyancy force. It could be positive or negative, depending on, as I mentioned to you. So since pressure in a fluid increases with the depth, the pressure on top is F top is lower, so the force F top is lower. The pressure on the bottom, F bottom, is larger. So since the bottom is deeper, there is more force pushing up than force on the bottom pushing down. And therefore, there is a net upward force which pushes the object up. That is buoyancy. And it's a function of the density of the object and the density of the fluid. So as I mentioned, the buoyant force is equal to the weight of the fluid displaced. So FB, the buoyant force, will be equal to FW, and that will be equal to m into g, where m is the mass of the object and g is the acceleration due to gravity. So density is equal to mass upon volume. Therefore, mass is going to be density into volume, and the force of buoyancy will be equal to rho into V into G, where rho is the density of the fluid, V is the volume of the body, and G is the acceleration due to gravity. So please remember that the buoyant force is exerted by the fluid, not by the object. There is a strong misunderstanding many people have that the buoyant force is subjected by the object. No, it's the fluid that gives the buoyant force, not the object. In fact, the formula that we need to remember is that the buoyant force FB is equal to rho of the fluid into G into volume of the submerged body. Okay, this is the master formula that we are going to use when we continue. Now, at this point of time, I am not able to see any screen, so therefore I am not able to answer any questions or take any questions. However, there are other people in the meeting who can answer questions. So I would request that they should take care. I'll be able to answer questions in the end. So coming back to the question which I raised in the beginning of the meeting, when will a body sink or float? It depends on a term called as lightness. So the lightness is equal to the buoyant force acting minus the object weight. And this determines if the object would float or sink. If lightness is equal to 0, which means the buoyant force is exactly equal to the object weight, then the body will be in equilibrium, as you can see on the soda can in the center figure, where the upward buoyant force is 3.9 newtons and the downward force due to gravity is 3.9 newtons. So the net force is equal to 0. Whereas on the left-hand side, we have a body which is heavy. The buoyant force again is 3.9 newtons here because somehow we are assuming that the volume of the fluid displaced by all three bodies is the same. But the weight of the body is 35 newtons. The force exerted by the body's mass is 35 newtons, which is downwards. And the buoyant force is 3.9 newtons. So therefore, we will get a net downward force of approximately 31 newtons, 31.1 newtons to be precise. On the other hand, if you look at the figure on the extreme right, where the buoyant force is same 3.9 newtons acting upwards, but the downward force due to the mass is only 3.5 newtons. So therefore, a difference of 0.4 newton upward will be acting. and hence this body is considered to be light. It will float. It will go up and float. Okay, and it will float to that extent that the two forces balance. Right? This is the basic principle of Archimedes. Now, using these principles, we can proceed to the aerostatics of airships. Maybe it's a good idea to stop here and to take some questions. So I'll just see if there is any question in the chat window. Anil Sharma wants to know, how will we generate buoyant force for an airship? Well, we are just coming to that. We're just coming to that. Okay, right. So let's have a look at the aerostatics of airships. So there are two terms in airships that I would like you to understand. The first one of them. Okay, so people are asking questions. First of all, I would not like people to attend as anonymous attendees. It's better if we know your name. So please don't attend as anonymous attendees. The two terms are very important when you look at the calculation of lift acting on a body on an airship. There was a question raised by a participant about how do airships generate lift. So I'm trying to answer that question here. So the first term that we have to understand is called as a gross static lift. And friends, you will also require this when you design your airship before you fabricate it. So please pay attention. So the gross static lift, actually called as LG, L gross, is equal to the buoyancy. Okay. The other name for buoyancy is gross static lift. So it is the upward force experienced by the airship by virtue of displacement of air with magnitude equal to the weight of the air displaced. So notice, if we have a body which is shrinking in size for any reason, then the force of buoyancy will reduce. And similarly, if we have a body of a given mass which increases in size, okay, due to, for example, because of high temperature or any other effect, suppose you have an airship which increases in size by 5%, then the buoyancy also will increase because more air will be displaced. So it is the volume of the air displaced that is important to generate the buoyancy force. Now, just like there is a concept called center of gravity of any body where we can assume the net mass of the body to act, there is also a term called as the center of buoyancy, or CB as we call it, which is the center of the gross static lift. And it can be obtained by locating the geometric center of the mass of displaced air. Just like the center of gravity can be obtained for any body by taking the sum of, you can do a summation of the moments created because of various parts of the body, divide by the total mass of the body. Similarly, you can actually obtain, Meenu, you have a question regarding lift. So please hold on. We will answer about these questions later. So center of buoyancy basically is a location at the center of the mass of the displaced air, which will be the location where one can assume the net buoyancy force to be acting. Okay. So for example, if you have an airship envelope where you have the force of buoyancy or the gross static lift as volume times the density of the air and into G, right? Where vol is the volume of the airship, rho A is the air density, and G is the gravity, then the gross static lift will be acting at the center, or can be assumed to be acting at center of buoyancy, CB. Notice that the density of the material of the body has no role to play. It is just the density of the air which is displaced and volume of the envelope, because it is the envelope and other components also which are displacing the air. Now we come to a more important concept, which is the net static lift, which is something that is available to us for putting any component or any payload on the airship. And that is the net static lift is equal to the gross static lift minus the weight of the lifting gas. So somebody asked in the chat window, in the question and answer session, about does the weight of the lifting gas inside the envelope also count? The answer is yes. It has to be subtracted from the gross lift to get the net lift. Okay. This also acts at center of buoyancy. So the net lift, which is of importance to us, will be the gross lift minus the weight of the LTA gas. So therefore, what you can do is you can call it as volume into, it's the weight of the LTA gas, which will be volume of the LTA gas into the density of the LTA gas into G. So when you do LG minus WLTA, you can get it as volume common rho A minus rho LTA into G. So this term rho A minus rho LTA is normally called as the lifting capacity of a particular gas. This value rho A minus rho LTA is the highest for hydrogen among the gases available today, and next to that is helium. But then there are many other gases which also have a positive value of rho A minus rho LTA, the lifting capacity, but it can slowly reduce. Okay, so here is an airship, and the gross lift LG is volume into rho AG, and the weight of the LTA gas is acting, and WLTA will be the volume into rho LTA into G. So it is this difference or the net static lift which is available to us. Now, if you look at the anatomy of a remotely controlled airship, which is what we are going to build, what we do is we mount. So we are going to make only what is called as a non-rigid airship. That means the envelope will have nothing inside as a solid member. It will maintain its shape only because of the pressure of the gas that we fill in. We will mount fins on the back to provide control and stability, as we will discuss in detail tomorrow. But if we do not do anything, then the center of gravity of this particular system could be located behind. Okay, because there are fins mounted behind, etc., etc. So what we do normally is that we add some ballast in the nose, or if required in the tail, to bring the center of gravity exactly below the center of buoyancy, so that the center of buoyancy and center of gravity are in the same vertical line. The purpose of this is to ensure that the airship, when it flies level, does not have any moments. So this is also a question asked by somebody, that when you are flying an airship at 500 feet altitude, how do you ensure that it flies straight? Well, you can ensure it flies straight by trimming it so that when it flies, there will be no net moment. Okay. Now ballast is required so that the airship can trim into a desired angle, preferably at 0 degrees, but maybe at a slight positive angle. That is decided by the user depending on what the airship is going to be used for. So when we look at the component breakdown of an airship, the weight of an airship, it will be equal to the weight of the LTA gas plus the weight of the envelope plus the weight of the fins on the back, which are, as I mentioned to you, required for controlling it and stabilizing it. And there is a gondola in which you mount all the equipment, the motors, the controllers. Then you have weight of avionics. And then we have the weight of ballast to trim. Now there is a question by Anirudh Sharma. Can we add heating coils or element to variate buoyancy as required by the user? Yes, it can be done. It can be done. And also Neeraj Kumar Mandlekar has a question about filled buoyant gas is measured by pressure. Normally, what should be the buoyant gas pressure regardless of airship size? So the pressure of the gas is normally about 500 Newton per meter square more than the ambient pressure. That is normally the one Normally that is the one. So that is normally the case. Okay. So now if we look at the static equilibrium of airships. So an airship is in static equilibrium if the total weight of the airship equals to its net static lift. So the weight of all the systems which I mentioned to you, if that is equal to the static lift, then it is in equilibrium. But an airship could be statically heavy or statically light. If it is statically heavy, then the gross lift will be less than the weight. And if it is statically light, then the gross lift will be more than the aircraft weight. So therefore, if the airship is statically light, it will tend to float up and not fly level, because it will tend to go up. And if an airship is statically heavy, then it will tend to fly a little bit down. Okay. So at this point, what I would like to do is I would like to just create one small poll for everybody. So I'll just stop the share for a minute. Okay, just bear with me for a minute. I'm just going to create a small poll just to check if you are able to appreciate what we have discussed so far. So right, give me 1 minute, please. Okay, so I'm going to launch a poll. Right, and okay. So I'm ready, and now I'm going to write. I'm going to allow you to answer the question. There are 210 people in the audience. I've launched a poll. I would like people to answer this question. Okay, around half the people in the audience have participated. I would urge maximum number of people to participate, because by your answers we come to know how much you are able to appreciate. So good, around 60% people have participated. I'll be happy if we go to at least 90%. I'll give another 1 minute before we stop the poll. So guys, please answer. There are around 209 attendees, and out of that, around 140 people have answered the quiz so far. I'll be happy if the number goes to nearly 200. It's a very simple question. Don't worry, there are no negative marks. So we have crossed 71%. That's a good number. Okay, I'm going to stop the poll in exactly 1 minute from now. So please answer quickly. Okay, so I'm going to end the poll now. So you can share, you can see the results now. Okay, now nearly 30% of the people are saying that they are flown in statically neutral condition. 26% of the people say they should be statically heavy, and the majority are saying that they should be statically light. So if there is anybody who is anyone who says that they should be statically light would like to unmute and speak. Can someone just type the reason why they should be statically light? You could answer in the question, you can just answer in the Q&A session. Why should they be flown statically light? What is the advantage? Someone can raise their hand if they want to speak. We will unmute you. Okay. Aman Dhiman, can you please? Okay, Chaitanya Bansal, can you please talk? I will allow you to speak.
Yes, sir. Sir, am I audible?
Absolutely audible, Chaitanya. What is your answer and why?
Sir, I think they are usually flown in statically light conditions.
Why is that so, Chaitanya?
Yes, sir. So, sir, it is needed to maintain buoyancy.
No, to maintain buoyancy, they should be statically neutral. If they are statically light, it means that the buoyancy force is more than the weight.
Okay, sir.
Yeah, so if that is the answer, then they're statically neutral. Okay, but okay. Anybody else? Prasad. Yes, Prasad, please go ahead. You can talk now, Prasad.
Sir, am I audible, sir?
Absolutely audible. Please go ahead. What is your answer and why?
Sir, if it is statically neutral, statically light, sir, the easily it can gain lift, sir. So no extra amount of energy is required, sir.
Yeah, but Prasad, if it is statically light, it is going to just keep rising up, na?
Yes, sir.
Do you want an airship to continuously keep rising up? Because buoyancy is more than the weight, so it is not. It's not going to fly level then.
Yes, sir. Sir.
Okay. We'll take a few more questions. I think Aman Dhiman, I'm going to allow you to talk quickly. Yes, please, Aman. Unmute and speak, Aman. Yes.
Hello.
Yeah.
Am I audible, sir?
Yes, audible.
Sir, I think it should fly in static heaviness condition because we can have a good control over the airship and a balanced landing we can do in emergency situation.
Okay, your answer is right. They are normally flown statically heavy, but I will like to elaborate a little bit more. Okay, Sparsh Ranaware. Sparsh, we are going to ask.
Yes, sir.
Yes,
Am I audible?
yes, audible. No need to ask the question.
Yes, sir.
Everybody-
Sir, I think it should be statically light because there are some conditions in the air. Due to some thermal changes, the air becomes rarer, and in such conditions, we would like to avoid crashes. And due to pressure changes and all, it is more likely be safe that our blimp or airship must be statically light to avoid accidents.
No, no, no. I don't agree with you. I don't agree with you because if you make it statically light, how does it become safe?
Yes, sir. Yeah.
How
that
does
was
it become
also
safe? Because it is statically light.
So it is only applicable for some points, but yeah, I agree with you.
Okay. Harshit Khatri, would you like to answer?
Yes.
Yeah. Yes, Harshit, sorry.
Sir, theoretically, it should be statically light to generate lift and in equilibrium to in static condition, but practically we fly it in slightly heavy condition because if anything wrong happens, we need it to come down, not go up.
Perfect answer. Harshit, I'm glad you have really answered it perfectly. We want to fly the airship slightly statically heavy so that in case we lose control or something happens, the airship can be brought down simply by their weight. So it's very interesting. We talk about LTA systems, but we cheat. We do not make it LTA. We fly it heavier than air. We fly it in a statically heavy condition, but that is only meant for operational safety. Correct. So you are right. Airships are normally flown in a statically heavy condition. Okay, this is the time now for us to take a short break. It's 8:21 by my time. We can take about a 5-minute break and then we can resume. So this is a 5-minute bio break. Don't sign off. The meeting can just go on. I'm going to simply mute the YouTube. Okay, so we meet after 5 minutes. And in this time, we will try to maybe answer a few questions. So see you in a few minutes. Okay, friends. So we are going to resume now and just continue from where we were. So the next thing is on airship sizing methodology. Okay. And I think for that, I'm going to invite Sohan to share the screen. Sohan, over to you.
Thank you, sir. So I think we can resume now. Do I start? Am I audible?
Just
Yeah,
before you
please.
start, yes, there is one question which we can take. As
Okay.
buoyant force is reactant force produced because of force acting on a body, is it possible if we apply a large amount of shear force suddenly, can we get more buoyancy? I don't know. Shear force direction, if it is upwards, maybe you can get upward force. Sparsh Ranaware has a question. I've heard about blimps. Difference between airship and blimps. Okay, it's called a BLIMP, blimp. Blimp is a colloquial name for an airship, just like we say drone for an unmanned aerial vehicle. Generally, blimp is used for airships which are called as non-rigid airships, which have no internal structure and they keep their shape only by the overpressure. So that is exactly what is meant by a blimp. Okay, right. So with this, over to you, Sohan. I'll take care of the question in the meantime.
Well, hello everyone. I'm Sohan Suvarna, and I hope I'm audible. So what Professor Pant spoke about in the previous session is going to be very useful in this session. So if you have any questions regarding that, please post them on the Q&A session. I have to apologize because I'm a little bit under the weather. I have a little bit of cough, so you have to pardon me if I cough during the session. So with that, let's start. So I'll be talking about envelope sizing methodology. Yeah, so we are only going to talk about the envelope in this particular presentation. So what is the methodology behind sizing an envelope? So the first thing we need is the design requirements. Excuse me. So the design requirements would mean that we need to know what the operation of the airship is going to be. So the first thing would be the payload or the mass. That is the thing that you want to carry on the airship. The next thing would be the size of the operating arena. Now we are designing an airship for an indoor arena. That's why operating arena is of concern to us. And then the speed. So let's say you're making an airship for Regatta. So speed is of a very important consideration because you want your airship to be fast. So these are the three important design requirements that we will consider while we design our airship. So many people in the Q&A sessions asked about what is the best profile for airships. So let's talk about the shape of the envelope. So ideally, we would want something which takes less space. So why are not airships spherical? Because if you have a spherical envelope, it would mean that you have lesser surface area. That is, the weight of the envelope will also be low because for a given volume, a sphere has the least surface area. Then also you have something called a skin friction drag. So this is the surface area dependent component. So if you have less surface area, it would mean that you will have lesser skin friction drag. Also, as I mentioned, for a given volume, it has the minimum surface area. So all this is an advantage of having spherical envelopes. However, we don't see many spherical airships, there are several structural advantages to a sphere as well. So one is that it gives you uniform internal pressure. So you have hoop stress, that is the internal gas inside the balloon. It's going to basically exert force outwards. So because of that, you will have some kind of a pressure inside the envelope. Now that is minimum and uniform for a spherical envelope. Also, there is no room for kinking. Now what kinking is basically this. So you have the airship, and let's say there is some drop of internal pressure in the envelope. Then what happens is, because it is shaped like this, a conventional one, you will develop some sort of a kink here. So this doesn't happen in a spherical envelope. So in spite of that as well, we don't see that airships are spherical. And as I mentioned, skin friction drag is basically because of shear stress. So whenever you have more surface area, you will experience higher skin friction drag. So that's what happens. These are all the pro points as to why we could have spherical envelopes. But we don't have spherical envelopes mostly. We usually go for something a little more conventional. So let's see why. So ideally, it's all about how the air flows around the airship. So let's say you have a spherical envelope like this shown here. You would want ideally the flow to be very smooth and just, flow like nothing has happened. There is no object in between and it's just smooth. And this kind of flow is called laminar flow. Unfortunately, this doesn't happen in real life. And what really happens is something like this. So when there is air, the arrow marks indicate the direction of the airflow. And what you see is that there are some recirculation here at the back of the spherical body. Now, because of this, what you have is something called as form drag. Now, this is purely because the air which is going around the ball, it's basically generating more pressure on it. So it's kind of contributing to the drag. So what is the solution for this? So what we would do is we would try and elongate this. So as we elongate the second half of the sphere, we notice that there would be lesser and lesser flow separation, or lesser and lesser vortices being formed at the back. So that is the reason why we ended up with this streamlined shape for airships. So ideally, you would want the shape to be something like the bottom right side. And yeah, so this would give you the minimum drag, and this is operationally very important when you are picking up an envelope profile. Yeah, so form drag is a function of, as I mentioned, flow separation, that is these eddies or the recirculation in flow that happens behind the object. And then it is a function of the shape. So as you can see, for sphere, you have the maximum, and as you streamline the body, elongate it towards the back, you have lesser and lesser form drag. And also the projected frontal area, that is the area that is visible, that is projected to the airflow, that also needs to be minimum. So that this is the main reason why we don't see spherical envelopes, rather we see something more like a streamlined shape. Now, what are some of the popular envelope profiles that we see? So one is the NPL. This stands for National Physics Laboratory, if I remember it right. So it's a combination of two spheres, two ellipsoids. So you have one ellipsoid here and the other one here. You can see that by the equations here. Okay, so it's just joined together in a way to form an envelope profile. And then we have the GNVR. This is our personal favorite in our LTA lab, mainly because this entire structure is made out of simple geometric equations, like you have the ellipse, you have the circle, and then you have the parabola. Then you have these Yuan shapes. Now, this is a little more elegant in the sense that some optimization was done for a particular Reynolds number, particular velocity that it's going to be operated at, and with that you get this kind of shape. Now, in our tutorial, in our sessions, what we will usually follow is the modified GNVR. Now, if you look back, GNVR shape, it's a little more bluff. So, as you can suspect from the previous slide, that is the slide on form drag, this GNVR is going to have a little higher drag. So what we do is we introduce a cylindrical section in the middle, and then we have the same GNVR shape, but in a modified fashion. So now you have an elliptical region, you have a cylindrical region, you have a circular region, and then you have a parabolic region. Now, for this particular shape, the reason why we like it is because everything sums up very, very well fit. For example, the envelope volume can be simply written in this form, in this particular equation. And the surface area also can be written like this. So all this are the reasons why we chose to go ahead with this particular profile for this workshop. But you can explore other profiles as well. The methodology, however, that we are going to present is going to remain the same irrespective of what envelope profile you pick. Are there any questions up till this point? So maybe Professor Pan can update me if there is something seriously to be discussed again.
Everybody, so on. Either I am answering the questions or I will let you know.
Okay, okay.
Just continue.
All right. So let's go ahead. And the next thing that we want to do is pick an envelope material. Now, what are the good features for an envelope material? Now, the first thing that you would want is that it should have low permeability to helium or hydrogen. That is, if you're making an envelope, it should be capable of holding helium or hydrogen. Basically, if you pack it in if you have a balloon or an envelope, you want the gas to stay inside, and it should not escape from the envelope. So that's the first thing that you're going to notice that you want to have in the material. The second one would be the sealing ability. That is, if you're not able to join the materials together, you won't be able to fabricate an envelope. So this is the second most important thing that we look at. Are you able to seal in a known way the material that you have? It could be using heat sealing methods. It could be using adhesives. It could be using radio frequency welding. Any of the sealing methods that there exist, if you're able to seal them, and if you have the ability to seal the material, then it's a reasonable material to go ahead with. The next thing that we want is that the fabric density should be low. Now, fabric density is basically how much does your material weigh per square meter or per square unit. So basically, you want it to be very light. The envelope should take as little weight as possible, so that you have more lift for the other important components like your payload, or maybe for carrying some battery or the other structures. So for that reason, you want the fabric density to be as low as possible. The next one is the flexibility. Now you need to be able to fold and work with this material in a way that when you inflate it with lifting gas or even with air, it needs to take the shape of the envelope. That is the envelope that you desire. So it needs to have that flexibility. And the last one that we look for is the tear strength. So basically, if there are some kind of holes or even a small tear in the envelope, it should not propagate. Typically, if you look at some materials and if you, let's say you have paper and if you poke a hole in that, it's not going to propagate because it has a higher tear strength. But the same thing, if you do it with a lace wrapper or a packet of chips, if you just take the packet of chips and you poke a tear in there, or poke a hole in there, and you pull the bag apart, the tear will propagate. So that is not something that you would look for. So you want something, you want the material to also have a good tear strength. Now, what are the options that we have for envelope materials? What are the candidate materials? So one of our favorite ones is the metallized polymer. So it has one layer of metal and one layer of polyethylene tetraphthalate. So basically this material, the reason why we like this material is because one, it is light. Two, it is very strong. Three, it has a very good holding capacity of lifting gas. And it's also easy to work with. And bonus point is that it's very cheap. A roll of this, you would probably get it for maybe 2,000 rupees. So it's very cheap as well to work with. Then you have low density polymer, that is LDPE or low density polyethylene. So this material is what you normally see around when you have, it's the usual plastic that you get in the market. So it is also one of the good candidate material. However, we don't usually go for it because it tends to be slightly higher mass than metallized polymer. And also we noticed that the sealing capability, even though if it seals well, the risk that that seal would break is quite a little bit higher when we work with LDPE. The next one is polyurethane. Now this is a very good material for airships. Even I would say even better than metallized polymer because it is more durable as compared to metallized polymer. It's also stretchable. Unfortunately, this also happens to be one of the expensive materials. So that's the reason why we don't usually go with polyurethane. And it's also a bit difficult to locate around your surroundings. So this is one other material that you could go for, polyurethane. And then we have some elegant materials which are basically engineered for airships. So one option is PU coated nylon. So in this, you have one coating of polyurethane, which would be your gas holding layer. And then you have nylon for strength. So when you combine these two, you basically get the best of both worlds. So you get the strength from nylon and you get the gas holding and the permeability qualities from polyurethane. So these are the kind of materials there are. Apart from this, there are many other materials such as PVC, the usual PVC. You can make them, but they are heavier, and many more materials can also be engineered for this purpose.
So before you go ahead, there is a question on the previous slide about the shapes. Can you go back to that slide, please?
Yes.
Yeah, there is a question, I think the next slide, that you have a circle and somebody wants to know where is the radius of this circle?
So you see this equation here. So you would have to get it from this equation, this R of x that is equal to square root of this. I cannot really tell you at this point what it is because I just made it simpler so it's easy to work with. But it's going to be, it's basically just an arc. So your radius, your center of this circle is going to be quite far.
Yeah.
Yeah.
That's right. That's right. It's an arc of a circle actually. It's an arc of a circle and you can calculate the arc length by, the radius by solving the equation for maximum diameter. Take it as unity and solve it, you will get the value.
Yes.
Okay. If somebody has raised the hand, I would request people not to raise hands, but simply type your question in the question answer window and we will try to answer it. So on, go ahead.
So don't worry about the shape that you see here. We will revisit this again tomorrow while we are doing the tutorial. In fact, what we are also going to do is we are going to code this entire equation, the entire profile in an Excel file. And you will have a step-by-step guide as to what you need to do before you size an airship. So you can hold your questions, but if you cannot hold them, please feel free to ask them in the Q&A box. Okay, so we covered this. Now the next part in the methodology is to do component weight estimation. Now, apart from the envelope, you have many other things such as the gondola. Gondola is basically the place where you keep everything in the airship. So that would be avionics, which is basically the electronics that you need to fly. Also the payload and even the propulsion system. They all come inside the gondola, and gondola itself would have some kind of a structural weight. Then you have fins, which are basically for stability. So you need to be able to fly it in a very controlled fashion, or so that's why you need fins. So they also contribute to the weight. And as I mentioned, avionics, which is basically the electronics, the motors, the propellers, the radio frequency, receiver, and the other electronics that are associated that are within the airship. So all this come under avionics. And then, as previously Professor Pant had mentioned, we also have ballast. So this is basically something that we use to balance the airship when it is flying, or even when it is static. So all these components you need to know the not know exactly, but at least have an estimate of what these weights are going to be before you actually size the envelope. So all this are required. Now the detail of this, I'm going to cover it in tomorrow's session, because each of this will take some time in understanding what is the weight component that goes into it. So we will cover this tomorrow. So let's assume for now that we have the weight estimate for all of this. Okay. And let's go ahead with the envelope sizing methodology. Now, Professor Pant had already spoken about static equilibrium. That is basically the difference between the total gross lift, the gross aerostatic lift, and the weight of the airship. That is basically if these two balance out, then it is basically said to be in a static equilibrium, and that particular size is known as critical size. And we also saw about static heaviness, and as Professor Pant already discussed, that we want to fly airships in a static heaviness condition, wherein we have gross lift lesser than the weight of the airship. Now, what we can do is we can define, we'll just revisit some of the concepts that was covered earlier. So we have the gross aerostatic lift, that is LG, in this case, the total buoyancy force, the blue arrow. So that is a product of volume, density of air, and gravity. Okay, very simple. Then we have net aerostatic lift, which is basically the difference between the total buoyancy, the gross buoyancy, and the weight of the LTA system. Now the gas inside the envelope is also going to have some kind of a weight. So for example, if you have helium, it would approximately have a density of 0.2 meter cube. So if you have 1 meter cube, the helium gas inside would weigh 0.2 kgs. Okay, because the density is 0.2 kg per meter cube. So any kind of lifting gas has its weight. So that is why we have to subtract that. So when we subtract that, what we have is the total available lift that we can use to support the structures and the payload of the airship. So that is defined as net aerostatic lift, and that is the difference between total gross aerostatic lift and the weight of the LTA gas. Now, we can just simplify it to get this equation, which is volume into the difference of densities multiplied by gravity. So this was also covered previously. Now, what are the components for airship weight? So this was also shown earlier. So we have the LTA mass, we have the envelope weight, we have the fin weight, we have the gondola weight, we have the propulsion mass, the payload mass, and the ballast mass. Now, the weight excluding the LTA gas, let's just call it W dash. What we do is we just take WLTA to the left hand side, and we have this W dash, W minus WLTA. So this is basically all the components except the lifting gas, the weights of all the components except the lifting gas. So now we define this term heaviness, which is basically W minus LG. Okay, so W is the weight of the airship and LG is the gross aerostatic lift. Now we define this term as H. So when H is positive, it means that it is statically heavy, which means the airship would automatically come down if there is no force acting on it. However, if H is negative, it means that it is statically light, which means it would go up, the airship would go up. And if it is 0, it means that it is neutrally stable, it is neutrally buoyant. So let's just substitute the terms in this equation. So W, we can write it as W dash plus WLTA. Okay. And LG, we just retain it like that. Now W dash, WLTA minus LG is nothing but minus LN. Okay, so it's just this term. So that's why what we have is this condition, which is the net aerostatic lift LN should be equal to W dash minus H, where W dash is the weight excluding the LTA gas, weight of the airship excluding the LTA gas, minus the desired heaviness. So we just write it in this fashion. So this forms our basic criteria for the sizing methodology. This is the equation that we are going to use again and again until we reach the point of our design, until we reach our design point. I'm hoping that everybody followed this slide because this is going to be very important. If not, you can ask me questions later as well. I don't mind going over this again. Okay, so let's go ahead with the sizing methodology now. Now we have this condition ln equal to W dash minus H. So the sizing methodology would start with simply inputting a sizing parameter. So in the case of modified GNVR that you had seen earlier in the envelope profile, that parameter would be the maximum diameter. So any given envelope would have some kind of a sizing parameter. And if say you have, if you don't have anything, you can just rely on using volume as a sizing parameter as well. So initially what you do is when the start of this algorithm, you just guess a value for a random value for the sizing parameter, any value. And the next thing you do is, because you know the equations for the volume and the surface area of the envelope, you compute the surface area and the volume. Okay. And the next step, because from the surface area, you can calculate the envelope weight, which is nothing but the surface area multiplied by the fabric density. Okay. Then with the volume, you can calculate the aerostatic lift, which is basically volume, which is the equation for this ln. Volume into difference of densities multiplied by gravity. Now you have the structural weight estimated already. And if you sum up the envelope weight and the structural weight, what you get is the total weight W dash. You guess here you get W dash, total weight excluding the LTA gas. Now, if you take the difference of this aerostatic lift and total weight, what you get is the net aerostatic lift Ln. Okay. And then you compare, then you see whether this condition is met. Is Ln equal to W dash minus H? If this condition is met, it means we have reached the optimum condition, but that wouldn't always be the case. So if it is not the case, then you have to appropriately change the sizing parameter and repeat the process again. Okay, you repeat the process again until you get until you meet this condition, that is Ln equal to W dash minus H. And once you meet this criteria, you would just output the sizing parameter. Does that make sense? Any questions on this? Okay, so I'm assuming everybody follows this. So in the tomorrow's session, we will be doing airship sizing. We will consider a sample case. We will we will lay out the design requirements, and we'll use this algorithm to size the airship. The floor is open for discussion now.
Yeah, what I would request is let people ask questions first. Okay, so there are 3 questions. Anonymous attendee says, can we get these slides? So my answer is, don't talk unless you put your name. Okay. RP wants to know, is a non-symmetric shape used on airship so it can generate an additional lift force like aerofoil due to its shape and angle of attack? So Sohan would like to answer. This is a very good question. Yes, thank you for that question. Yes, there is a class of airships called as hybrid airships. So typically, well, although hybrid airships are not technically lighter than air because they derive part of their lift from buoyancy. Part of their lift from aerodynamics. So I would urge you to look for Airlander. That is right now the world's largest aircraft. So you can have a look at that. It's one of the
one of the airships which doesn't have a symmetric envelope. It's basically a set of 3 envelopes put together, and then you have this big envelope which also looks like a wing from the sides, and it generates lift while flying, aerodynamic lift while flying. So it is possible, and it's currently in development.
Okay, just do me a favor. I'll share my screen and show you. You can stop your screen sharing, Sohan, for a minute. There you go. Can you see the shape?
Yes, sir.
This is the airliner, a double blimp. This is a non-symmetric shape in many ways. You can call it symmetric across the center line, but you can see that it is flattish, just like you mentioned, Abhi. And we have recently finished a PhD on what is called as a tri-lobed airship design. So a student has finished PhD on that topic. So yes, the answer is yes. Tri-lobed or multi-lobed shapes can be considered for airships to provide a flatter surface so that the solar panels on the top are more effective. So that is the answer. Okay. I'll stop the share now. Okay, then is there a Liebeck profile airfoil type result for optimal airship profiles? No, this question is not relevant, Girish, because as I mentioned to you, we don't go for aerofoil shapes. Yashas wants to know approximately what percentage of an airship's lift is coming from lifting gas during a typical cruise. The answer is around 85% for a conventional airship. 85% or 90% lift will come from the buoyancy, and the remaining will come from the dynamic force acting. Sohan is answering the question regarding heaviness decision. That's fine.
So for heaviness, the question is, how is the heaviness decided for an airship? Well, if you are making an RC airship, I would say typically you should account for maybe about 10% of the 10 to 20% of the total buoyancy force that you have. That's like a ballpark figure. But more accurately is after you design the airship, you have put all the components. You would basically put things, put ballast in the airship and see what works the best for you. Because in the end, it's all about fine tuning. And in the design process, it's all about estimating what could be the likely heaviness mass. I hope that answers that question.
Yeah, so a good suggestion by Sohan is ballpark is you design your airship with around 20%, 15 to 20% static heaviness. That should be good enough for your application. Academia labs currently working on airships in the world. Okay, there are many of them. And our lab in LTA systems, IIT Bombay, is one of the labs working on that. And I can talk to you offline about the details. Sparsh has a very interesting question. I've heard about a material, micro lattice, being used by Boeing company, lightest material in the world. I would like to ask, can we use this material for airships to increase efficiency? The answer is yes. Any important material development immediately is utilized by aerospace engineers for improving. Tejasri Venkat wants to know, will we get the important slides which will be useful for tomorrow's lecture? Sohan, what is your take on this?
So it wouldn't be necessary because we again have all these slides covered when we are doing the tutorial. And also because we have the videos online, you can always revisit them and have a look at the slides. However, what would be shared is an Excel file, is a spreadsheet which would help you to size your airship.
Okay, so you will get a spreadsheet from Sohan to size your airship. Tutorial tomorrow, you should be working with us, isn't it? You should be calculating things as we go. Anirudh Sharma has another question. Is there any airship which uses propeller to control thrust and lift generated for airship, and will it increase the efficiency? So the answer is yes, we also are going to use one small propeller based motor to produce additional vertical force. What is the right/common safety factor for the design of an airship? Structurally speaking, the factor of safety is similar to the aircraft. We use nearly 3.5 to 4 factor of safety, but It keeps varying from component to component and application to application. Okay, I think that's all the questions we have. Okay. Right. Okay, now if there are no more questions, then what I have done is I've created a small quiz just to check how much you have understood. So I'm going to launch that poll now. Okay, I'm going to launch that poll. Unless Sohan, you want to discuss something else?
No, nothing else. So unless there are no questions, we can go ahead with the polls.
Okay, there is only one poll which is remaining, which I'd like to.
So there is one question which I'll just answer while you create the poll. So the question is, what is the difference between brushless outrunner and coreless motor, which we would be using in our airships? The answer to this question precisely would be answered on day 3. That is when we talk about the avionics of the airship that are in the airship. So you will have to hold your question until then.
Okay, great. So fine. So now I'm going to now launch. Oh.
So the other question is, flying whales are planning to use water as additional weight to make static heaviness and release it to reduce weight. Any other possible methods to reduce weight? I think Professor Pant has a very good answer for that.
Well, there are many ways in which we can go for weight reduction. I mean, there is a whole course we are conducting on LTS systems in which we talk about measures used by designers to reduce the weight. Okay, so it will be difficult for us to answer such generic questions in this particular session. I would request you to focus your questions and queries only related to design and fabrication of remotely controlled airships. Okay. So that would be easy for us to handle. I know there are generic questions you may have. I know you have generic questions, so I can understand that. But I would rather limit our discussion to the topics which are relevant to the current workshop. Okay, so I'm going to launch a poll for everyone. There are 5 questions. Of that, one of them has already been answered by you, so I'm repeating it just to check your memory. And then there are other 4 questions. So please answer the questions of day 1. Can you see the poll? Yeah, people are answering. Okay. So around 12% of people have answered the questions. I have request other people to also quickly answer so that we can then stop today's discussion. Okay, we have crossed 50%. 103 people have answered. So 2 out of 3 participants have answered so far, but I would prefer if more of you answer so that we can stop the discussion. So another 5 minutes max. We have just crossed 70%, which is a good sign. Requesting some of the panelists also to please attempt the questions. So 3 out of 4 participants have answered the poll, which is good. What about the 4th guy? Remember, we are going to use all this information to generate the attendance. Couple of minutes remaining before we stop. So Vedant Kulkarni has a question. How have any airship designs been found or studied in ancient Indian scriptures, which can be used even today? My answer is no. I don't have any idea about this. I have not seen. Okay, I think it's time for me to end the poll. 84% people have participated, which is not a bad idea. It's a good one. 152 out of 180 people have taken part. So I'm going to end the poll. And I would like to share the results with all of you. And then we will quickly look at what people have answered. So the first question is about statically light or heavy. And I'm surprised that 24% of people still feel that airships are flown statically light, and 7% people still feel that they are flown statically neutral. We have clarified, and we will like to clarify once again, airships are normally flown in statically heavy condition, so that in case there is a loss of control, we can bring them down. The next question is, why do we insert a constant diameter section in GNVR shape? The correct answer is to improve its aerodynamics and not to lower the envelope weight. In fact, it will increase the envelope weight because you are going to have a larger constant diameter. And also, it does lead to increase in length, but that's not the reason. And I'm glad that nobody has answered about looks. Which is the recommended material for envelope of an indoor remotely controlled airship? Sohan has mentioned in his presentation very clearly. Sohan, would you like to just confirm what is the correct answer?
Yes. So as per the options, in the options given, polyurethane is the best material.
Yeah, but that is not recommended by you because it is very expensive.
Yeah, but the other option should be metallized polyethylene. I think there was a typo there.
Okay, fine. Right, then let us look at the next one, which is the highest in magnitude. So yes, it is gross static lift. I have typed it twice, okay. And why is ballast used? Okay, so some people said to generate higher buoyancy. I don't know how it can be. How to make it light? It's not possible by using ballast. It will make it only heavy. To improve structural strength, that is also a guesswork. So some of you are not really paying attention, but bulk of you are paying attention and you are answering the questions correctly. So tomorrow we are going to conduct many such polls. So please pay attention. Before we go, we have already ended today's session. Vignesh wants to know any preferred color for airship to take temperature advantage. I would say make it white in color if possible. Please, if you can tell the process to register and attend tomorrow's seminar. And they are same. No registration is needed. Just join the link like today. Okay. We can handle 500 people in this meeting and only 250 have joined today. So many more can join. Tushar wants to know, you didn't explain about how we structured it. We'll do it tomorrow. Tomorrow is the session when we do today. Okay, before I go, I want to pass on the control to Dr. Manish Tripathi, who is the technical chair of an international conference coming up. Manish, you can share the screen and show the video. And after that, I'm going to give some closing remarks for today's session. So over to you, Manish.
Thank you very much, sir. So I'll just share the screen. Yeah. So
just talk about it first. Talk about it first, Manish. Just a minute.
Basically, I'm a postdoctoral fellow carrying out my research under Professor Pant at the LTA Systems Lab. And I'm also basically a technical committee chair for an upcoming event related to LTA systems called the Delta S 2022, which is an acronym for Design and Engineering of Lighter Than Air Systems. So this event is going to be conducted in the IIT Bombay campus between June 22 to 26. 2022. And basically this event will be encompassing a lot of technological activities related to LTA systems, including a series of parallel technical technical paper presentations, technological showcase driven by many companies who are venturing into the LTA systems, like the Blimp airships, the Flywin, and many other companies. There will also be we will also be conducting two sets of panel discussions, which will be embarked upon many eminent personalities related to LTA systems. And on the final day of the event, that is on the 26th of June, we will be conducting a regatta event wherein all the interested participants can participate in that event. They can basically design their airship. The airship designing methodology, this particular workshop that we are attending right now will be is going to be a good opportunity for you, wherein you can actually learn how to design the airships for that RC airship competition. And through that experience, you can design your airships and also compete in that event. So that regatta event is now regulated by the international sporting body called the FAI, and is also being co-hosted by the Aero Club of India. So these are some different ventures in that system. And for to create more hype about this, we made a promotional video related to this, which I would like to show henceforth.
Can you also share, Manish, can you also share the website?
Yes, sir.
Just show the website.
So for all the interested attendees, I'll just open the website and share the screen. Yeah, so this is the website, and basically the call for papers that was presented to you in the video, that has already been over, but we are still open to people enrolling for particular attendance during the event, and also the regatta event. Also, we will be conducting a pre-conference workshop wherein a sponsor company of ours will be demonstrating how their software tools can be used for carrying out CFD and fluid structure interactional study related to airships. This will be a good study for all the interested participants. So yeah, this is the, and I will
yeah, I'll just try to add, the main thing for students is this pre-conference workshop on 22nd of June. It's a one-day pre-conference hands-on workshop in which Metacom Technologies will demonstrate how their tools like CFD++, CSM++, etc. can be used for analyzing LTA systems. Okay. So they're also saying that you bring along your CAD model and they are going to probably try and analyze it right in front of you. So can you flash whom to contact regarding the workshop? Just scroll down, please. So there is a dedicated person who is responsible for contacting the workshop. If you want to take part in the workshop, please send an email to Shashwat Trivedi at 2040-10003@iitb.ac.in and also shashwat.airships@gmail.com. Okay, and also the Regatta page, of course, can be shown because they are already aware about it. Yeah.
So all people, concerned person can follow this link to carry out registration of their, so they can basically act as a student attendees also. And yeah, we are open to that particular venture.
So all the students, please note that the early bird registration is only open till the end of this month. If you register after 1st April, you are going to pay 2,000 rupees per day. Whereas if you register before that, you save 500 rupees per day. You could also register for the entire conference like few of you have done already. And then you'll get the advantage of 5 days at the cost of only 5,500.
Just to give you a small glimpse of what you get by just attending the conference. So these are some of the keynote speakers, and more of them are about to be added. And there will also be some technical showcase demonstrations by our sponsors, including those of H Aero, Imperial Galaxy, and Blimp Airships. So yeah, so all the attendees, they will gain a lot and get a lot of technological knowledge from this particular event.
Yeah. So check out www.deltas2022.in, which Sohan has already shared in the screen, and contact us for any queries. For the regatta, we are inviting teams of up to 4 students to register. Right now, we are just going to do just registration. Click on registration. Yeah, this is something that they should like to know. So there is a Google form which you have to fill up. This is a pre-registration form just to tell us about your interest. Go back, please. Main thing is I want them to see about, yeah, just read this. That's it. Just stop here. Yeah. So this is what you are able to take part. If you are interested, you can take part. We'll give you 1 day for practicing on 25th Saturday, and the conduction of the event will be on 26th of June, sorry. And the whole exactly 3 months from now is going to be the regatta. So we have started this workshop today because we wanted to give you 3 months time to get prepared for the airship. Okay, 26th June 2022 is going to be the regatta, and today is 26th March. So we hope you guys will form your teams of up to 4 people and register for the regatta and take part.
Furthermore, all the participants will be getting mementos, as well as the winners. They will be along with getting the award. They will also be listed in the FAI website, which is the international governing body related to air sports activity throughout the world.
Okay, so on that note, exactly at 9:30, we would like to stop today's session and request all of you to join again tomorrow. And if you have some friends who could not register today or could not join today, you are welcome to share the link with them. Anybody can participate in this 3-day workshop, and there are no charges, as you know. So please, we have 500 seats available on this particular webinar. And if it exceeds 500, we can easily watch on the YouTube. So a very good night to all of you from India, and good day to the others from abroad. Thank you so much. If there are no questions, I would request, I would close the session. Anybody else would like to say something? Any of the panelists would like to add something? Okay, so it's 9:30 in India, and so I will be stopping the